So the next analysis that was performed was the analysis to determine the maximum payload mass that could be flown to optimize the launch score. So this year for the competition, the maximum score was the sum over all 3 launch attempts of the total passenger meters, which was taken as the product of the number of TIMs and the distance traveled by the vehicle. So naturally, we wanted to find what combination of TIMs maximize our score, because the distance traveled is a decreasing function of the number of TIMs flown. However, there is one catch, and the catch is that if you fly less than 60 meters, you don't get any points for that round. Naturally, we don't want that to happen, so the goal was to find out how many TIMs we could fly just so that we flew over that 60-meter mark. The analysis was performed by changing this payload mass variable here. We iterated over 5 TIMs. Each TIM weighs approximately 125 grams. And then the multivariable iterator nested for loop was set up and run for all configurations of the rocket from 1 to 6 TIMs. The output was similar to that of the graph shown in the previous video, where we plotted the initial water mass on one axis and the launch angle on the other axis to determine the distance traveled at every point. The analysis showed that with 6 TIMs, the rocket would not make it over the 60-meter mark. With 5 TIMs, we would make it over the 60-meter mark, but just barely, only by a few meters. We deemed that the margin of error on the simulation was great enough that we might potentially fly less than 60 meters with 5 TIMs loaded in the rocket, so we decided to drop to 4 TIMs, which did cut the score in terms of the passenger meters because of the reduced number of TIMs, but did ultimately increase the total distance flown on every single flight and ended up netting us a second place finish.